On this video, I want to look at conservation of energy or mechanical energy from the point of view of projectile motion, because we've come to have a pretty good understanding of projectile motion, and I thought we could take that as a sort of basis or foundation to build our understanding of conservation of energy. So, from what we know about projectile motion, if I start the projectile, let's say it's an object that has a mass of 1 kilogram, and I want to use 1 kilogram because it's nice and easy to work with. I'm going to launch it here at 25 meters per second, 30 degrees from the horizontal. Now, if it lands at exactly the same height, I know it's going to also land with a velocity of 25 meters per second. Whoa, that's pretty rough. Anyways, you get the idea. It's 25 meters per second, and that is also going to be 30 degrees from the horizontal here. And so if I look at it from a conservation of energy, and I use these numbers in my 1/2 mv squared, whatever that number would be, I would obviously get the exact same number plugging in these before and after parameters. Now, usually what we do from here is take this initial velocity and break it up into its x and y components. So if I choose maybe a green color here to show the y component, and maybe sort of pink color here to show the x component. Might be hard to see, but there's my x component of that velocity. I'm going to solve for those, so my vx is going to be 25 times cos of 30. That's going to give me approximately 22 meters per second, and my y component is going to be 25 meters per second times sine of 30. That's going to give me roughly 12 meters per second here. And with these values, I can now start doing things. I can now start solving, for example, for the maximum height. Using Kinematics equation, it's pretty straightforward. We know we can plug in some numbers and get those values. But let's solve it trying to find the maximum height using conservation of energy. Now, conservation of energy, we usually look at or start it by saying here that all my energy total in the beginning has to equal all my energy total at the end. That's the idea of conservation of energy in an isolated system. And we do make the assumption that this is an isolated system, so sound and friction, all that kind of stuff doesn't really affect the system here. All the energy in the beginning would be my kinetic energy in the x, and I'm going to break it down into x and y, and you'll see why in a second. So kinetic energy in the x component plus kinetic energy in the y component plus gravitational potential energy in my initial position. And that's got to equal all the energy at the very top here as it's conserved. So once again, Ek in the x component prime plus Ek in the y component prime plus gravitational potential energy prime. Once again, my prime right now is I'm talking about this point right here, which is the maximum height of my projectile. Alright, what do I know? Well, my Ekx over on this side, I know that velocity doesn't change throughout the whole projectile because there's no force acting out, no work is being done, so the energy is not changing. So the Ekx before and the Ekx after or during or anywhere along this projectile is always going to be the same value. So effectively, they cancel each other out, and I don't have to worry about them. Which is nice, because really, when I solve for this type of question using kinematics, for maximum height, I always use it in the y component, because a height is a y component, and so the velocity that I would use for that would be the y component. And that's what I'm going to use for my EKY here. So this will become 1/2 mv squared plus mgh equals 1/2 mv squared, squared prime plus mgh prime. And I know that my velocity at this particular point in time in the y component at the top of the projectile is 0. So that will take care of this term. And my my height at the initial position is 0. I'm starting from the ground, or a frame of reference that I've chosen to be 0. So this becomes 0 also. And I'm left with 1/2 mv squared is equal to mgh at the maximum height. If I plug in the numbers for this, 1/2 times 1 kilogram times, in the y component, it was 12 meters per second, so if I take that number squared, that's 144 meters squared per second squared. That's just velocity squared. That equals 1 kilogram times 9.8 meters per second squared times h, which is what I'm trying to solve for. I'm going to take out my calculator and see that h is equal to 7.34 meters. Another way of looking at these exact same values from a sort of different perspective is to actually solve for how much energy does the system have in the y component at the initial projectile here. So with our 12 meters per second, how much energy does that convert into? So essentially my system in the y component, EK in the y, is equal to 1/2 mv squared. V is 12 meters per second, m is 1 kilogram, times 1/2. I have 144 divided by half, 144 times a half. That gives me a value of 72 joules. And this obviously should work out if I plug in my mgh over here, because I know all of my kinetic energy at the top of the projectile is 0 meters per second, therefore it's 0 joules, then m times g times h should also give me 72 joules. So 1 kilogram times 9.8 times the value here that I've solved for, 7.34, should give me 72 joules, and I'll let you guys figure that one out. And just to see if my initial answer was correct here, I had solved that the h value, the maximum height, was going to be 7.34 meters. Let's double check using kinematics equations that we normally use for projectile motion. So here we have the formula Vf squared equals Vi squared plus 2ad. At this maximum point here, we know that Vf in the y component is 0. Vi squared is going to be our 12 meters per second. Once again, keep in mind I'm using the y component only right now, 12 meters per second squared, plus 2 times negative 9.8 meters per second squared times d. If I solve for this, my 12 meters squared becomes negative 144 meters squared per second squared on this side. That's looking very messy. And then 2 times 9.8 negative gives me divided by negative 19.6 meters per second squared, and I solve for a d here. So essentially, the negatives cancel out. I have 144 divided by 19.6, and according to my calculator, that is approximately equal to 7.34 meters. And that's the displacement in the y component, which is beautiful, which is why physics is beautiful. And the last thing I'm going to do here on this video is look at another type of question that might be asked. What if I asked, instead of solving for the energy at the easy parts, where it's at the initial where there's no gravity, or at the top where there's no kinetic in the y, what if I ask you for, I don't know, this spot right here at 2 meters in height? My question to you is, what's the velocity at this point in time here for this object? So I know that looks like a 12. I'm just trying to show the height here. At this height of 2 meters, how fast is this object going? Well, just like with forces, we started with free body diagrams. In energy, I always suggest starting with all your energy that's involved in this system. And I say ET is going to equal to ET prime, so before and after sort of thing. Total energy, initially, I've got kinetic energy in the y, plus kinetic energy in the x, plus gravitational potential energy. It's going to equal kinetic energy in the y, EK y prime plus EK x prime plus EG prime. Of course, there's a few things that we can cancel out, which is always nice with these energy type questions. First of all, I'll cancel out gravitational potential energy initially because I'm starting from the ground, so it's 0. I'm also going to cancel out my 2 kinetic energy in the x's because those are just going to give me the exact same value twice. I can't even decipher which is which here. Let's just say it's this one. That's my x, this one is my y. And then that's it. So I can sort of simplify this equation to say ek in the y component is going to equal ek in the y component prime, the after, plus the gravitational potential energy that it's gained. And that should make sense, right? It's slowing down as it rises up in the y component, so this is going to be less, this kinetic energy is going to be less, and it's gaining gravitational potential energy. And because of conservation of energy, the two values added together are going to equal my initial kinetic energy in the y. So I'm going to start plugging in numbers here. 1/2 mv squared equals 1/2 mv squared plus mgh. I can cancel out all my m's, they're all equal to 1 anyway, so it doesn't change the overall magnitude. I'm going to have 1/2 times 12 meters per second squared, which is 144. So once again, I've got 72 joules for this kinetic energy is going to equal 1/2 times my velocity squared plus mgh. So that's, or sorry, gh, I've canceled out the m, so it's going to be 9.8 times 2 meters, so that'll be 19.6 joules of gravitational potential energy. I'm going to bring my 19.6 over to the other side of the equal sign to start solving for v. So that's 72 minus 19.6. And then I'm going to multiply the whole thing by 2 and find a square root to find a velocity at that point. And I get a value here of 10, or roughly 10 meters per second. Just to make sure that the answer makes sense, remember the y component, I started off with 12 meters per second. I'm slowing down. I'm going to a maximum of 7.3 meters. So at about the 2 meter mark, I shouldn't be too far off from my 12 meters per second. So the answer makes sense logistically. One more thing, I just realized, I know I said I canceled out the m's, and then I'm still working with joules here. Technically, if I want to work with joules, then I need to keep the m's in place. I need to have a kilogram, for the unit of joules is equivalent to kilograms meters per second. So there you have it, using projectile motion and conservation of energy. Hopefully this video has made a little bit of sense to you and helped you with your basic understanding of these two concepts.